This last video for chapter 5 is lesson 6, which is direct variation. The essential question: how can you use a graph to show the relationship between two quantities that vary directly, and how can you use an equation? So I started off by reminding you how to find slope, because we're actually going to be using that again today. Remember, that's your difference in y over your difference in x, so we subtract two y values and subtract those two x values. And then we have some new vocabulary. We've got direct variation, which is the equation y equals kx, where k is a number that is not equal to 0. So this k here in the equation can never be 0. What this equation does for direct variation is shows a proportional relationship. And if you remember, a proportional relationship is a straight line that cuts through the origin, which we call 0, 0. I want you to copy down that definition of what direct variation is, and always remember that this is the equation for direct variation, y equals kx, and always remember that k cannot be 0, and that this equation shows a proportional relationship, which means that it is a straight line that cuts through the origin when you graph it. Then we have a constant of variation, which I have the definition in blue. In that direct variation equation, y equals kx, k is the constant of variation. K is also just the slope of the line. Right? It's showing that direct variation. It's showing how it's changing constantly. It's just the slope. It's how steep that line is. It's showing that change. Okay, so right now you are copying down those definitions. If you need to pause the video until you get it done, please do that now. Our key idea is just, again, going through what direct variation is, that y equals kx, where k is a number that is not equal to 0, and k is also the constant of proportionality. When it comes to the graph of kx is a line with a slope of k that passes through the origin, which just means constant of proportionality. It's a proportional relationship. See how you can hear that word proportion in constant of proportionality. So if we look at that graph that they gave you as an example, you can notice that it is a straight line. It has a constant slope, and it's cutting through the origin. Therefore, it is showing direct variation. It's showing a proportional relationship. So we can come up with the equation that they used for direct variation, y equals kx, and come up with that equation that actually matches the line, so that for every x and y, we can figure out what it is. And all we would have to do there is find the k, and we know that k is really just the slope. So how do I find the slope of this line? Well, one way would be to pick 2 points. So I have the origin, because it's cutting through the origin, and I also have that other point there. So my 2 points that I'm choosing, 0, 0, and 1, 2, I can do it by counting right on this graph, since they're all one box is 1 unit, which means vertically I'm going up 2, and horizontally I'm going, over 1, which means my slope is 2 over 1, so k is really 2 over 1, or simply 2. So if I want to come up with an equation that matches that line, I would say y equals 2x, because 2 over 1 is just 2. And in that equation, y equals 2x, 2 is the k. It's the constant of proportionality. It's also the slope. So k is really slope. Right? That's one thing that we want to remember. That will help you to very easily come up with an equation for direct variation of a line. So moving on to an example, identifying direct variation. It says, tell whether x and y show direct variation and explain your reasoning. So they have a table for part A, where x is 1 and y is negative 2, x is 2 and y is 0, x is 3, y is 2, x is 4, y is 4, and they graphed each of those points on the coordinate plane. They then drew a line through those points. So looking at that graph, is that direct variation? Well, we know in order for it to be direct variation, it has to be a straight line that cuts through the origin. And there's your origin. Is that line cutting through the origin? No, it is not. So this is not direct variation. Explain your reasoning. Well, what would my reasoning behind it? It is a straight line, but it's not cutting through the origin. So your reasoning would be it does not cut through the origin. Both things need to be true in order for it to be a graph of direct variation. We know that the origin is 0, 0. If I look at part B, again, I've got my ordered pairs 0, 0, 2, 2, 4, 4, 6, 6. They graphed each of those ordered pairs. They drew a line. It is a straight line. It is cutting through the origin. So this one would be a yes for direct variation. And my reasoning would be it's a straight line. And also, it cuts through the origin. All right, so it follows the definition of direct variation. It also follows the definition of a proportional relationship. So that's why they call it constant of proportionality. All right, so you can see the difference between part A not being direct variation and part B being direct variation because it is a straight line that cuts through the origin. All right, so I'm going to ask that you guys graph these guys on your own and look at your graph and decide whether or not they are showing direct variation, and then explain your reasoning. So support your answer of yes or no. All right, in order to do that, you're going to have to really pay attention to your x and y axis here. In the first one, since you have a y of -2, you're going to have to move your y-axis and your x-axis over a little bit. So in order for you to do that, you're not going to use the actual outer part or outer edge of the graph as your axis. You're going to have to move it over a little bit. So I'm going to create my y-axis here. Just to move it over. And since y is -2, that means we're going to be going down. Just move your x-axis up a little bit so that -2 will fit. So redraw that guy with a new x and y axis. In the second one, you've got a y going up to 16. So make sure that you have enough room to fit 16 up there. So you're probably going to want to count by 2's on your y-axis. So 2, this would be a 4. 6, this would be an 8, 10, 12, 14, 16. You're labeling those axes counting by 2's so that we can fit this 16 there. And x is only going up to 4, so you can count by 1's on your x-axis. And then the last one, you have x's that are negative, which means you're going to have to move that y-axis over enough to fit up to -2. So I'm going to move my my y-axis over a little bit. And you can actually keep your x-axis at the bottom. All right, so this is now y, and this is x, y. All right, now that they're labeled, I'm going to ask that you pause the video, go in and graph those ordered pairs for each of those numbers, and decide whether or not your graphs are showing direct variation. So in number 1, I'm going 0, -2, starting at the origin. For x is 0, that means I don't move left to right at all. I'm just going -2, which would be down 2, which I'm going to do in a different color so you can see it. So here's would be your point for 0, -2. Back to my origin, 1, 1, I'm going right 1, up 1. 2, 4, I'm going right 2, up 4. And 3, 7, I'm going right 3, up 7. 1, 2, 3, 4, 5, 6, 7. I then have to have a straight edge. I cannot do this by hand because it might be very close. So by looking at that without the straight edge, you might have said, oh, it looks like it's going to cut through the origin. But once you actually draw a line with a ruler, is it cutting through the origin? Did we hit here? No, we did not. So this is not direct variation. And your reasoning would be, it doesn't cut through the origin. In number 2, remember we count it by 2's on that y-axis so that we can get up to number 16 that we need it. So I'm going to start at my origin, which is in the corner here, and I'm going to go over 1 and up 4 for my first ordered pair. 2, 8, I'm going right 2 and up to 8. 3, 12, I'm going right 3 and up to 12. And 4, 16, right 4, up to 16. Grab that straight edge that we need, drawing a line through the points and extending it. And see, I'm even off a little bit there. I gotta move this over to make sure I'm cutting through all the lines. And even when I do that, I can still see, did we hit that origin? Yes, we did. Therefore, this one is showing direct variation. And reasoning would be straight line through 0, 0. Through the origin. And then in our last one, where we moved that y-axis over to the right a little bit so that we could have some negative x's, we're starting at the origin where the 2 red lines meet. -2 for x means you're going to the left 2, and +4, you're going up 4. 1, 2, 3, 4. That would mark us there. -1 for x means from the origin you go left 1, and +2 would be up 2. 0, 0 we know is our origin, which would be there. So far, does it look like direct variation? It certainly does. But then we get to 1, 2. So back to the origin, we're now going right 1 and up 2. So if I were to try to make that a straight line, it starts out as a straight line, then it curves up to look like a V. So yes, it started straight, it is cutting through the origin, but then because it cuts up and it looks like a V and it's no longer a straight line, this would be no for direct variation, and your reasoning, not a straight line. Right, so we can see the difference where in number 1 didn't cut through the origin, so no for direct variation. Number 2 was a straight line cutting through the origin, so it follows the definition, so yes, it is direct variation. And in number 3, no, because it's not a straight line, it's starting to look like a V. Moving on to example 2, we're going to identify direct variation. So we know from the very beginning in our vocabulary that the direct variation equation is y equals kx, where k is your constant of proportionality, or basically just your slope of the line. So what we need to do is we need to get y alone in these 2 examples and see, does it follow the definition of y equals kx? So if I were solving for y in part A, I'm going to get y alone. So how do I get y alone here? I need to subtract 1 from both sides. Do the opposite of adding, or inverse operation. We subtract 1 there, and that would leave me with y. And since I subtracted 1 on that side, I need to subtract 1 over here, which I can't do to the 2x because they are not like terms. So we're just going to rewrite it as crossing that out, making it y is equal to 2x minus 1. So does that follow y equals to some number times x? No, it does not, because it has this extra piece here. It has this minus 1. And there's no minus or plus in the kx part. It's just kx. It's just a number, a slope, a constant of proportionality times x. So this guy would not be direct variation. Notice again it says explain your reasoning. Your reasoning would be it has subtraction. There's no subtraction in the direct variation equation. So since this one has subtraction, that's why it's a no. In the second one, this one's a little bit more tricky. We're going to solve for y, so we've got 1/2 times y. Well, what's the inverse of multiplying by 1/2? That would be to divide by 1/2. We're using those inverse operations to get that variable by itself, that y. We're solving for y. I'm drawing my line because if I divide it by 1/2 on that side, I must divide by 1/2 on this side as well. So that leaves me with y is equal to x divided by 1/2. So when I first look at that, does that look like y equals kx? No, it doesn't. But what do we know about dividing by a fraction? Can I change that to keep change flip where I would make it a multiplication problem. Right, so think about that. This is really x divided by 1/2. So I'm going to come up here and write it. X divided by 1/2. If I were to rewrite that, that becomes x times 2/1. I just changed it to multiplication, which is what I need. So this is really y equals 2/1 times x, 2/1, or simply 2, times x. Now does it look like direct variation because of our rules for dividing by a fraction? Keep, change, flip, making it multiplication. Now I'm taking a number and multiplying by x. So now this is a yes. So I want you to copy down this set of notes here. When x is the numerator, here I had an x of a numerator, it can be rewritten, it can be rewritten as multiplication showing direct variation. So copy that down, that's very important. So even though it looked like a division problem that we would say, nope, not direct variation is when we multiply a number by x. As long as x is up top, we can rewrite it as multiplication. So whenever you have x divided by something, you're going to rewrite it to show multiplication, which would mean that it is always direct variation. All right, and your reasoning behind here, this yes, it follows y equals kx, where 2 is k. All right, so give yourself a chance to copy that down so that you have it in your notes. Pause the video for a sec so that you can do that. Then you're going to work on your own problems, where you're going to do exactly what we were doing up in the example A and B from example 2. You're going to solve for y in each of them. You're going to see, does your equation follow y equals kx? That's what we're looking for, y equals kx. So get y alone in all of these problems and see if it is showing direct variation. I'm going to have you pause the video, solve those for y. Make sure that your yes and no has a reasoning behind it. You always must give a reasoning as to why it is or is not direct variation. So in that first problem, to get y alone, I have to get rid of multiplying by x. So to undo multiplying by x, we're going to divide by x on both sides. They cancel out, leaving me with y equal to 3 divided by x. Right, now notice up in our notes we said when x is the numerator it can be rewritten. Is x my numerator here in number 4? No, x is my denominator. So just to prove that x has to be the numerator, watch what happens when I try to rewrite that as multiplication. That says 3 divided by x. If I want to change that to multiplication, it becomes 3 times the reciprocal of x, which would be 1 over x. So that's like saying 3 times 1 over x. Should be writing with this multiplication. Now, does that look like kx? No. So since x is my denominator here, this is a no. It does not follow y equals kx. Right? That follows y equals k times 1 over x. That's not our definition of direct variation. In number 5, to get y alone, I'm being multiplied by 1/3, therefore I'm going to divide both sides by 1/3. Right? These cancel out, leaving us with y. And then we're going to do x divided by 1/3 on the other side. So notice I have x as my numerator. So thinking about that as a division problem, x divided by 1/3 gets rewritten as x times 3/1, which we could say is really just 3x. And if that's equal to y still, I have y equals 3x. Does that follow y equals kx? Certainly does. 3 is your k here. So this becomes a yes, follows y equals kx, even though it's written the opposite way, it's still the same, we can change that, where 3 is k. So 3 would be our constant there. Okay, so notice that we wrote that in our notes. When x is the numerator, it can be rewritten. We had x as our numerator there in number 5, so we can make it direct variation, y equals kx. In number 6, to get y alone here, I need to subtract 1 from both sides. That leaves me with y is equal to x minus 1. Does that follow y equals kx? No, because again, it shows subtraction. There's no subtraction in direct variation. All right, so that's the end of direct variation. Your equation for direct variation is always y equals kx, where k is just your constant of proportionality, also known as your slope. The graph of direct variation shows the graph of a proportional relationship, a straight line that cuts through the origin. Things you want to remember from this lesson.